come to the Vintage Computer Festival at the Enter Museum to see the evolution of From the Hole to the Cloud.
Okay, it will be in English now, so I'll make a short introduction. Jean-Daniel Nicou contacted us, the IEEE Life members. You know, IEEE is a very, very large organization all around the world, 500,000 members, they say now, just recently. And it's organized with technical societies. So you have a computer society, my society was solid state circuits, you have communication, you have all sorts of societies, very specialized technical societies which organize conferences, publications, and all sorts of things. And also you have standards, which are another thing. And then you have local organization. There is a IEEE Switzerland, and IEEE Switzerland, there is a committee and they organize things. And inside Switzerland, we have so-called chapters. Chapters are the reflection of these technical societies. And we have a chapter about solid-state circuits, for example, and industrial electronics and so on. And also, there is a student branch in ETH Zurich and École Polytechnique Lausanne. There is a so-called Women in Engineering activity group and so on. And there is Ruby and I are from the IEEE Life members, which are the members who have more than 35 years of membership and more than 65 years of age. So here we are. And Jean-Daniel contacted us saying, why don't we organize something here at Enter, between Lausanne and Zurich somewhere, to talk about the history of computers in Switzerland specifically. And here we are. Thank you. Thanks to Jean-Daniel. And thanks to Enter. When we talked with Enter, they looked at the calendar and said, yeah, good idea, but let's do it in common with Vintage Computer Festival, which I think is fantastic because it brings more people and different generations as well and different interests. So here we are, and the date was defined already early in the year. So Daniel Borel, founder of Logitech, unfortunately he left. He's on travel. He left 2 days ago, and he could not join. So he said, "Okay, what can we do? Can we do video conference?" I said, "No, I'll be traveling." So we did a video recording for 37 minutes, and I managed to make it shorter to 25. And I found it quite interesting, and you will hear this when the machine is starting.
Hello everyone, I'm happy to be with you today and share half a century of a unique period of my life, which covers the beginning of the microprocessors all the way to the digital world which we know today. For me, it started at EPFL. I had a couple of courses in electronic digital from Professor Nicou, which was certainly a precursor in all what did happen in this part of Switzerland. And I finished my study in plasma physics, and plasma physics at the time was a lot about simulation on computer, and I did work for half a year, 3/4, when eventually I realized that my professor told me that plasma physics would eventually become real 25 years from at that time. I found it too long, so I decided to make a jump and to look into going to the US. I got a scholarship from the Fonds National de la Recherche Scientifique. This allowed me to go and study in the US for 1 year at Stanford University, and this was the time, 1976, when the valley was on fire. I would say we had many Jean-Daniel Nicou in Silicon Valley. Everyone wanted to create their own company to invent the future, and it was extremely exciting. It was a time when you had the first single-board computers with the 8080 microcomputers and 8088, 8086, Zilog 8088. It was just amazing how buoyant it was this time in the industry. Everyone would believe he could invent the future. This is also the time when Microsoft in '75 was created, then Apple in '76. And then it was a mix of hardware and software with VisiCalc, which was a major thing for Apple II, which became a computer, a microcomputer used in businesses as well. And for me, the study at Stanford University really allowed me to meet a friend of mine with whom I created Logitech afterwards, which was Pierluigi Zappacosta. And before that time, when we finished our study with our master, but we had an idea, and the idea was at the time, this will make you smile, that typesetters or typewriters were going to be replaced by a computer where you could type a letter, type a document. Our angle compared to other competitors which already existed in the US was to address ourselves to the European market with all the different languages. So I came back to Switzerland, my friends stayed in Palo Alto, California, and we looked for money. And I still had, before finding the money, to find a job to feed my wife, but also my newborn child in 1977. And I found Bobst Graphics. And Bobst Graphics was pretty unique in its way because they were starting in this industry here of phototype setting. Our goal was more word processing, less ambitious than phototype setting. But after a while, I realized that discussing with them, we could eventually mix our own dream of making a word processor, competing against the world, even though we were very small, thanks to our knowledge of languages. So I made quite a deal with them, so by which I would help them on one side, and on the other side, eventually, after a while working with them, I would get a sponsor from them to go back to California and develop what we call the Bezy. Bezy was for Borel Zappacosta, my friend, spelled B-E-Z-Y, and we had a budget of, I guess, 30,000 Swiss francs from them to be able to build a computer and to program a computer. We had 6 months. So after 6 months, we came back, presented the device very proudly to the management of Bobst. The reason why we were able to make it so fast is because at the time microprocessors were mainly programmed in microprocessor language, assembler, which was very lengthy and very difficult. As software engineers, we very quickly use a high-level language to program those little beasts, and we were very, very fast to do so. After a few years of development, unfortunately, it was the 1st of April 1980, I guess that Bobst Graphics management decided that maybe the dream and the goal was a bit too complex and not very profitable. So they decided to refocus on their main business. Our system, the system we had developed by the 1980 April, was one which was pretty sophisticated. It was not just a typewriter or word processing system on a computer, but we had all kind of an operating system. We could do accounting, we could do many other things, spreadsheet running, and so on. The one thing which was our luck is that in April every year you would have the CeBIT show in Hanover, and at the time, in order for us to simulate the output of a typesetter, the typesetter, which is those machines which allow you then to print the book and so on, was to be able to have a typewriter with a daisy wheel, and you could program the daisy wheel, so you can kind of simulate the output of a film machine just with a word processor. This printer we had chosen by chance was from Ricoh of Japan. And so Ricoh stopped by to see their customers. We were a very small customer. It was April, I guess, 15, 1980. We had just been told by management that we had 1 month to find someone to buy our system back, 1 month for 1 million. And then that was a rush for us to try to find someone to save 3 or 4 years of hard work, day and night. And luckily enough, those Ricoh people stopped by. We didn't tell them that we had a problem, but we were dreaming with them because they had a large contract from Hitachi in Japan, and what they wanted to develop was not a word processing system, but a graphical editor with a large screen, and because they had a contract from Hitachi for making a patent editor with picture and everything. It was very the early days. And beginning of September 1981, Ricoh gave us the contract for a feasibility study of a graphical editor, which would have by chance also a mouse, because the mouse was the only way to actually really move a cursor on the graphical screen. Thanks God for us, we had again Jean Daniel, who was ahead of everyone, I guess, and we were lucky to be able to access this device and to include it in our feasibility study for Ricoh. The study took about 4 months. We gave our report. In the meantime, we created Logitech on October 2nd, 1981, because to sign a contract, we had to have a company for such a large customer as Ricoh. And then we waited to see if they liked it or not. And eventually, February 1982, they said, well, it's fine, it's great. We are going to give you a contract. We are going to go forward with this project. But we would like the development to take place in Palo Alto and not in Switzerland, because Ricoh, we have in San Jose a Ricoh company who could be close to Palo Alto, and our team could work with your team. So eventually, we installed ourselves in the small office in 165 University Avenue. If you go on the internet, the 165 University Avenue, the first company who was there was Logitech, then there was Google and PayPal. So for us, a new story started, which was being in Palo Alto. And in Palo Alto, we had a software team developing things for Ricoh. Was back in Switzerland. Nobody knew if my wife would be able to pay the salary for the family to live, or if myself would be able to sustain my job, if you want. So we started we continued the Logitech here. Here we looked for jobs like with Omega Swiss Timing. We did the development of system hardware and software for the Olympic Games, including 1984 in LA. And on my side, I couldn't just accept that, I was away from Logitech US and growing Logitech. So the mouse became the real thing which I could work on. And thanks God, the lab of LAMI had a terrific engineer, René Sommer. And René Sommer, who left after too early, unfortunately, was the person who took the original mouse of Jean Daniel and added a microprocessor, so the mouse could be programmed in some way. And this mouse was available from him in 1982. I said, what do I do? But we were Stanford students, and as Stanford student, we had access to Arpanet. So eventually we saw on the Arpanet that some people were looking for mice. So on one side, we had this project of Ricoh, which was designed around the mouse. But then to go further, it was interesting to see, could we eventually find a market for this little mouse? And so I went back to my professor at Stanford, who just said, well, I know a lot of people in the industry, and it's the beginning of graphics. And this professor was very well connected, so eventually he came up with a long listing, I think that's thick, of all the companies he knew in the US who would do graphical work. Guess what? In the same way there was Cebit in Europe, there was Comdex in Las Vegas. And I remember going to Las Vegas and with this long listing of companies and going with a bag of mice that René Sommer had prepared for me. That was just to say a point in the history. It was the very beginning of VisiCorp, VisiCalc, which is a turning point in the personal computer industry because it was a spreadsheet. And spreadsheet became really the first piece of software beside editors that people would be using a computer for. And actually this was a great success of Apple II. And eventually you go booth after booth, and little by little we found traction of people who really wanted to get mice from us. I think that one of the things which was great from the design of Jean Daniel and the LAMI was that the mouse itself It was a mechanical mouse, but it was also a mechanical mouse, but optical decoding, which make it longer in life because the other one has a little drum and the contact was physical and would wear out, so it was not as good. So we had an angle to attack the market and say, hey, you know, we are Swiss, we know how it should be done. It's like a watch, the inside was like a watch, and we got some credibility. So Jean-Daniel gave us a little company in La Vallée de Joux, Desprats. He said, you know, you can go to them and start having them manufacturing it. You know, we were software engineers, so we could design software, develop software for the mouse, drivers, or even application like word processing application or text editor, which would be kind of fun. We had those experience for that, but manufacturing, we had no clue whatsoever how to manufacture anything. The only problem is that the Desprats company had some problem. It had some problem because each time we would get a shipment from them and ship it to the US, where our market was, it was only the US market, the mice arriving on the other side would get rusted. And after maybe 6, 9, 12 months of customer of ours, you know, they were small customers buying maybe 10 mice a month or 20 mice a month and so on, and they were returned, half of them. We said we cannot continue like that. And we couldn't continue like that because in '84, the lack struck. My professor contacted me one day and said, you know, it was the beginning of the PC. You know, 1981 is the first IBM PC which came out. So actually Logitech was born the year of the IBM PC, was our lack as well. And he said, I have a contact at HP. HP was just launching the HP 150, where they had two kinds of interface. An interface with a mouse or an interface with a touchscreen. Of course, today it looks like something everyone is used with their pad and so on, but at the time it was not that common. So HP had taken this angle, but they needed a mouse. So we went to them and they said, your mouse is really great, the technology is good, but you know, we want our own shape and we want you to manufacture it for us. 1983, we went to Cortaillot, and after a while we were not very satisfied. The price, the cost of it was just too high. We needed to break their contract. We came back, they came back to us and said, if you don't want to work with us anymore, you need to pay us 1 million. And having escaped Bobst Graphics with a 1 million to buy back our software, so we're back with a 1 million. But this time we felt that it was really, you know, maybe worse because with a customer like Hewlett-Packard, which was a great deal. So that's the time when we eventually decided to do it and take our destiny in our hands. And we started to manufacture our own mice in Apple. Apple, which is a small village where Logitech was kind of created. Apple Village turned out to be the Apple manufacturing place. We had rented places in the different buildings. We started to make our old mold. We use some subcontractors, and the whole thing turned out to be reasonably okay. You know, we found ourselves as software engineers going into manufacturing. The reason also why we got HP was not only because the mouse designed by the LAMI was one which was maybe unique by the optical decoding, but it's also because we could develop software. You know, at the time there was basically, we went from alphanumerical screen, where there are only characters, to graphical screen, so there was not much experience. And thanks to the Ricoh experience we had, which was a graphical editor, we could develop a pretty nice text editor, which was for HP and others, AT&T, Olivetti, something. So little by little, we suddenly found ourselves with many suppliers, customers around the world, which was kind of, even IBM was a customer of ours. And one day we said, well, you know, we cannot be the mouse maker if we cannot make the mouse for Apple computer. And so we went, René Sommer went to Apple one day because, you know, in this industry it was so new. You would meet in show Bill Gates or Steve Jobs. It was not hierarchical. It was really a chaos which was creating and inventing the future. Already Microsoft himself were using mouse with Word because there was a Word with a mouse in May 1983. Certainly HP was the first step. And the second step would have been Apple. So our friend René took the case of a mouse of Apple and designed a new mouse for Apple. And René was a very fine person, a great engineer, very smart, and he presented it to Apple. And Apple came back to us pretty quickly and said, well, your design is great, that's what we want, but we want to buy from you the whole design and make it ourselves. Because your cost is too high, you don't know how to manufacturing and so on. Even so, we're manufacturing for HP, but those were, you know, small quantities, like 500 a month or something like that. And then that's where we took the challenge. We said, no, I think Apple offered us $100,000 to buy the whole thing and everything, and said no. And we said, no, we are going to make it ourselves. And so I went at the time throughout Asia. I went everywhere. We took a consultant, Baker & McKenzie, and they guided me around Asia. I went to Singapore, I went to Korea as well, I went to Thailand, I went to Hong Kong, I went to Taiwan. And eventually, at the very end, we decided that Taiwan was a place. And it was also the reason why, because we had a software engineer. You know, software was important for us in our office at Palo Alto. She was from Taiwan. So she said, well, you know, I can help you. And, you know, eventually we applied to the government because they had a south of Taipei, they had an industrial park, the Hsinchu Scientific Park. But to apply there, at the time it was only there the large companies. There was AT&T, there was Cum, there was many others, and they were never small, tiny company like us. And her angle to the government was say, well, look, this is a company which in the middle of all the other one will give our people, our young people in Taiwan, what Silicon Valley is today. And eventually it's interesting because maybe 10 years or 15 years after we were there, all the large companies like AT&T, like Cum and so on disappeared. And this park became really the park for the new generation of Taiwanese who had been studied in the US and were back there. For us, the Mars started to be very large as a business, except that it has never been a straight line. You know, in life it's never a straight line. I mean, clearly in 1988 we went public in Switzerland, which was interesting because we went public with only 2 times $600,000 investment. So we only took from investor friend and 1.2 million. While today you see people who raise tons of money to get something. We went public at 62 million Swiss franc of revenue. But from that time on, our revenue doubled every year. So we went from 62 to 124 to 200 million. And then the red carpet was given to us by the bank. We were very, very much known as a company, reasonably successful. We could develop not only the mouse, but scanners and other product. And unfortunately, 1992 was a big crisis in the computer industry because the manufacturers for the large company American, like the Compaq, like the Apple and so on, were all from Asia, whether from Singapore or from Taiwan. And they invaded the market with price which were cut by half. A PC from IBM or Compaq were costing like $4,000 to $6,000, and they came with a price of $2,000 only. So it was a big, big drama. So this is when companies like Compaq almost overnight started to lose money. It was also the time when Microsoft came up with Windows 3. That is all the PC who by the time, until that time, until the early 90s, you would buy a PC and you buy in the retail store a mouse. 1992, with Windows 3.0 being bundled with every PC, the volume of mice jumped to the roof, but the price had to be cut by 2. And this is, you know, usually, as they say in China, Wei Ji, any crisis is made of a risk and an opportunity. And this is the year when we decided that we had no choice but to move to China. And so we moved to China before anybody. And the rest is kind of history, because then we were able to surf the wave, and we are still alive today. But one of the things I'd like to say is the fact that Switzerland has been an environment which was great, because we were able to hire engineers which we never would have been able to hire in the US. Smart, well-educated, because clearly in Palo Alto, California, or in Seattle, they would go to work for Microsoft, for Apple, and later on for Google. Here we had great people. We had a model where we took many of those engineers, sent them to the US. We could attract the best because they wanted to go to Silicon Valley, which was very well known, and created for us a way to have a company which has no real headquarters. We have been as much in Switzerland as we have been in Silicon Valley, as we have been in China or Taiwan, as been later on in Ireland, which was a great place also. And in this aspect, I think that Switzerland has been great, as I said, from a training point of view. The university has been great, with also Zurich, ETH, but also Yverdon, the Technikum, where quite a few people we came and still with us 30 years after, longevity, EPFL, of course. But on the other side, the US has been, in an amazing way, impossible to compare. And I have lived the PC in the Valley, where everyone is kind of broke. We were kind of a unique case with Apple, with Microsoft to survive. But then the US, Palo Alto went down, it was gloomy and so on in 1992, when pricing of everything went down, attacked by and that's where internet came up. Then again, the same cycle, then Google came up in the same building where we were in 98. Then Facebook came there, then video conferencing came, and so on and so forth, up to today, the artificial intelligence is getting the Valley. I was there 10 days ago, and it's just amazing, and that technology has been what has changed the world and giving jobs which are well paid, jobs which are exciting because you invent the future. So I think that what I went through and I lived through was just exceptional, was unique, was amazing, with all those people inventing the future. Sometimes you fail, but as they say, you know, try and fail, but never fail to try, which is a concept we should have. We should also accept that sometimes it doesn't work and you can restart. That we have a unique opportunity to play a role in the world of tomorrow. And what we have thought it is history, I think should help us also understanding the future. I think for once, what has happened over the last 50 years in Switzerland should also guide us and give us hope that Switzerland can play a role in the world of tomorrow, in the digital world, which will be changing society, the way we work, the way we play, the way we communicate. Thank you very much.
Okay, so I think Marc Bidiville has lived all these years, and in fact, you started at Bobst Graphics before.
Yes.
Daniel Borel. Yeah.
Yeah. In fact, all Logic founders worked for Logitech. So,
okay. So please,
I'm just one of them.
Yes. So please, the floor is yours. Yeah. Do you want to go on the? Yeah. Mettez-vous peut-être ici ou sur la base, un peu plus haut.
Oh.
Voilà.
Okay. So you heard what Bobo said about Logitech. It was the organization level, the market level, and trying to be different and speak of other things, I will really go to the nuts and bolts. So I will try to describe how we were able to make mice, to make them cheaper, and thanks to this, remain on the market. For this presentation, I used some slides from René Sommer, so I think he devotes mention. Okay, I rewrote my CV in a slightly different way. You know, I was born in 1948, which is the year where the transistor was invented. In 72, I got my diploma from the EPF. And during the diploma, I was able to see the very first chips of 4004. And in 81, there was the creation of Logitech. And this was the year of the first PC. So this means that really my life evolved in parallel with the evolution of the technology. Just a quick mention of Doug Engelbart, another demo in '68, where Doug Engelbart described, in fact, what should be done, and it took many years to accomplish this, because at the time the equipment that was required, you can read the list here, that was for millions of dollars, more or less. So this was not available to put in your living room. So as it was told by other presenters, everything in Switzerland started from the Guignard mouse, together with Jean-Daniel. And here there is the shape, everybody knows. There is a mechanical unit, probably the very first prototype. And the last on the right is what André did. He made molds, and he was casting epoxy resin to make the parts. And you can watch the little spring here, which is typical watchmaker type of design. So this is René Sommer was at the EPF next to André Guignard, so he got a mouse and he tried to find improvements and better ways to use it, because the Guignard mouse was just a parallel output, so you have 4 signals for the optoencoders and 3 signals for the switches. So René had the idea of using a microprocessor to communicate with, for example, a PC, because the PC at that time had no mouse interface. And we tried many times to have computer manufacturers including a mouse interface in their machine, so we could sell a mouse, a good business, but it didn't work. So the solution was to use the serial port of the MBM PC, which was available, and to communicate with the mouse through the serial port. You will notice here the mouse has 4 potentiometers. These potentiometers are used to adjust the level of the sensitivity of the opto for the shaft encoders, because opto components have significant variations in characteristics. So you have to manage a way to make all of them work more or less the same, because for the 2 channels of one axis, if the one has a very high duty cycle and the other one has a very low duty cycle, the sampling by the microprocessor can skip some states, and in this case, the mouse does not work properly. You miss displacement or you move the wrong way. So this was a solution that was used at the time. Then Logitech decided to manufacture the mice by ourselves. We tried with by subcontractors and other solutions, but we had problems all the time. The reliability was far from ideal. So after starting production of our mice, in fact, the customers at that time were mostly OEMs, not large OEMs, but who could afford a mouse and a graphics screen to go up with it. It was the people with a lot of money, so it was workstation. It was not personal computers. The graphic system was not adapted and not cost matching. So we had, with these OEMs, we were able to learn all the things that should be avoided, like we had rusting parts, we had a lot of other technical problems that we, in the end, were able to solve. And the business of Logitech was mostly for OEM mice, and personal users were not interested at that time. It's stuck. Okay, so this is the next slide.
Yes. So before.
Okay. But with OEMs, in the beginning, the volume were small because it was a graphics station, which were reserved for the elite. And, but the volume increased. And some customers requested a large volume, especially the last one, Apple. Once we got their business, we really need to produce in volumes that looked huge for us at the time. But we decided to make some design choices, and one was to get rid of the potentiometers, because if you have to adjust every mouse 4 times just to get the correct signal, it takes a lot of time to process each mouse, and the manufacturing becomes very slow. So we found another solution by making some slots in the mask, narrower, and this provided kind of stability in the output from the opto that could be used for very well. One thing also we learned in production is when you produce mice, at the end of the line, you have to test the product, and the yield you get is very important, because if you want to produce cheaply, you have to have most of the mice you produce working at first trial. No correction at all. Correcting, repairing a mouse that doesn't work takes a lot of time. Makes the process much more complicated. So it's needed to have a very high pass yield. Another thing to ease the volume manufacturing is to reduce the number of parts. The less parts you have, the faster you process the product. And additional to that, for the design, it was the problem that a mouse is subject to fall from a table. And you can explain to people they have to put something underneath to absorb the shock. You will not convince anybody. So the mouse has to be able to drop by 1 meter on concrete floor. So this was real rough, especially for mice that had a ball with a steel core, which was quite heavy. So this is like a bomb, like when the mouse crashes on the floor. Okay, now designing a mouse, it's difficult to take advantage of the Moore's law. People designing memories, graphics, every 2 years you double the size of the memory, doing nothing. But for a mouse, okay, maybe you will get a cheaper microprocessor. This helps a bit, but you don't get the help from Moore's law very much. Okay, fast assembly I mentioned before. Also, we tried to have standardized components, to use the same components everywhere for all the mice, for the different OEMs. The case was different, but the components inside the ball mechanics were the same. The switches also. We had to work very hard with the suppliers. So this was done first in Europe, but mostly in Taiwan afterwards, where they have to eject parts for us. And you have to design your parts in such a way that injection can be done easily with minimum cycle time. You know, you have the press that injects maybe one or maybe a few parts at the same time. And the cycle time is maybe something like 1 minute. But if you have complicated design, it can last longer. So, of course, the production rate decreases and the parts get more expensive because in a part, the price of the part is the plastic you put in it, but our parts are quite small. But also the time of the machine, because when the injector is doing your parts, he's not doing parts for someone else. So you pay. Also, we tried to have a smooth transition between generation of, we try to make evolve the design, but we try to remain compatible from one to the next one so we could switch easily because we made many changes. So here is an example. Oh, the title are completely off here. This is the evolution of the Apple mouse we did for the Mac SE, so it's ADB mouse. It was in '85. And the first one was using a ASIC made by Apple because ADB bus was kind of special and it was difficult to manage. So they designed an ASIC. The mouse looks pretty simple, but the problem was that the ASIC did cost a lot of money. It was quite complex, but so it was too much expensive. And this is where René came into action, and he designed the second one. The second one is using a standard microprocessor from Motorola. And what he did in this processor, he did the same that he did for the RS-232 mouse. You generate the signal, the transmission signals, by the microprocessor. So you have the microprocessor shaking the lines according to the specification of the protocol, of course, and communicating with the host. And people at Apple were not convinced that this was possible. So René took it as a challenge, and he did it. And this mouse is very simple, very cheap, but this was not enough. So a little bit later, in '88, we switched to a smaller microprocessor. It was a very crude microprocessor because it was a 4-bit microprocessor with 1K ROM and 16 bytes of RAM. So he wrote the code for this, and he was able to convince Apple that his timings were meeting the specs, and we started producing this one at a much lower price. And the last one, I will mention later for the mechanics, it's another further slide, but we simplified quite a lot the structure. We had a cheap Motorola microchip, which was at last available. So we were able to reduce the cost of the mouse. For your information, the price of such a mouse was about $1. So this was the price of one of the switches of the very first mice, almost. We used some Burgess switches at the time, and $1 a switch. So with $1 a mouse. But some people were selling the computer with free mouse. So making the free mouse, you have to be cheap. So this is interesting because this is a big change in Logitech strategy. Till then, we were working with OEMs, but the PC was there for a while, and people were trying to connect mice to their PC. So we decided to enter the retail market. So this is an ad on the right here. This is an ad that was published in Byte magazine. All the old people know about it. And this was really well known and a reference in the domain. And for this, René designed the C7. And the C7 has an important difference in the structure compared with the serial mouse he built from Guignard Mechanics, because it doesn't have a power supply. It does not need a power supply. The power supply is taken from the signal, the RS-232 signals, with some voltage converter, some diodes, and a lot of tricks. But he was able to draw enough power for the mouse through the RS-232 signals. But for this, there was one requirement which to reduce the power requirement, the opto could not be on all the time, because the opto LED need a lot of current, something like 20 milliamps times 2. So this is a lot of current. So he introduced the switching of the opto. So when the processor did not need to read the opto, the power was of the LED was off. And just before reading, he switched them on, read the data, and switched off again the LEDs. So this pulsing allowed to save a lot of current. And after that, enough current was available from the RS-232. So, and this mouse was a great success, because I remember we had ladies on the phone, answering the phone and taking orders for 1 mouse, 2 mice. So this was really the beginning of the retail market. And at the time, most of the screens were alphanumeric. Graphic screens were crude at the best. And it remained possible to control some application like spreadsheets or word processor using the mouse to move instead of moving the cursor with the keys. So this, okay, one other thing important was to have some sort of hysteresis. Before, the opto were always on, and the receivers we had were had the Schmitt trigger built in. So it was easy. But when you start to pulse the opto, you have to find ways to provide a kind of hysteresis. It's no more the hysteresis of a Schmitt trigger, but it has to be done by firmware. So this was done by firmware, by creating a ramp with the output of the phototransistor and taking many samples, or at least 2, and after selecting which sample to use as a function of the previous state of the same channel. So this made a way to push in the direction of the state of the previous reading. And it requires significant change in the amplitude of the signal to switch to the other value. Also, this LED pulsing was interesting because of battery-powered mice. At the time, René designed only one mouse for Metaphor, which was powered by batteries. It had 4 nickel-cadmium cells, and it lasted 1 day. But he had the feeling, and was convinced that one day it would be required. So he decided to work on this pulsing, and he spent a lot of time to find a good solution, which he did. Okay, so here it's a description of the mechanical part, the encoder. So again, the dates are completely off. So the first one was, in fact, very similar to what André Guignard did. Instead of having metallic and disc and mask, so the disc and mask, these are the disc, of course, these are the masks. The masks are used to generate the difference of phase between the two channels. So here you have the number of parts, and you can imagine the assembly where you have to take the long shafts here to plug them into the disc. Then you take the masks that you plug into the base here. Then you take a roller and you place it at its position, and you insert the disc with the shaft into the roller, and you press, and everything fits together. And you have to do the same for the other side. After, there is a fork, which is placed here at 45 degrees, that press the ball against the two other rollers. So this fork requires a small shaft put into a roller, then inserted in the fork, and then you insert the fork in the base, and you attach the spring. So you can imagine the time required to assemble all this. So we did also, you have 4 opto components. So there are 4 LEDs and 4 sensors, phototransistors. And here was the second step. We found a way to, instead of having the masks and separate LEDs for 2 channels, we put inside the sensors here, the 2 sensors. In fact, there are 2 sensitive areas which dimension, in fact, correspond to the slots that were in the mask. So this means that you can remove the mask, and you remove also 2 LEDs. You have 2 sensors here which are a little bit more complicated because instead of 1 phototransistor, there are 2. This is not huge difference, but this is a reduction. And here, instead of having metallic shaft and separate disc, roller, and shaft, it's all in one piece. So to assemble the mouse, you take a disc roller, you plug it into the base from the bottom, you take the second one, you plug it in, and then the fork is still a bit complicated, but the small roller for the fork also has shaft ends in plastic. So it's much easier, you plug it in the fork, and then you assemble the fork, the spring, in the previous place. So you can see the reduction in part numbers, and you can easily imagine the reduction in assembly time. And the last thing was that, in fact, this is a big plastic part. It's expensive plastic. So we said that let's get rid of it. So what we did, it's a case bottom. And in fact, this base is built into the case bottom. So you don't need this part anymore. You have the roller disc shaft combination very similar to those. And the fork, it's also the same with a larger roller. The opto remains the same. Il y en a encore. Non, il n'y en a pas beaucoup. D'accord. On va aller vite. Okay, so this is the same exercise we did for hollow mice. So again, the first models had a roller that was a completely assembled unit. Then again, we moved the slides for the roller into the base of the mouse. The roller was supported by a small support with the shaft. And this spring was used to make the ratchet function, and this spring here was used to lift the roller up, so you could press it down, and it was and the last solution we found here, instead of having these slides in the case bottom and this support, we built, in fact, like a third key in the middle that included the guides for the wheel, and there was space just for one spring for the ratchet. And that's all. So again, huge simplification and cost reduction. So this, quickly, it's the reduction for the opto. So this one we named Janus on the left, has the 2 phototransistors. And after that, we decided to try to improve because of the dispersion in the amplitude of the signals, and it was kind of a problem also. So we decided to build a sensor that, instead of using one phototransistor for each channel, we had 2 that were out of phase by half of the disk step. So in fact, one of the sensors was in full light, while the other was in the dark completely. And the value of the signal was deducted by comparing these 2 signals, which one is the largest. So this solution was used in shaft encoders, sold for a few $100. But here we were able to make it into a sensor that costed less than 10 cents. And a funny cost reduction, the sensor here, it's a new version of the sensor. The difference is not very important. In fact, this one has only 3 pins and instead of 4. So with 4 pins, you have the 2 output signals, normal, plus 2 power supplies. For this one, we decided that we keep the 2 power supplies. It's not possible to get rid of them. And the last one would be used in sharing for the 2 bits. So the processor read the value of the output, then it sent a pulse on the line, and the sensor switched to the other output. So with this, we saved 1 pin. And we heard at the time that the cost of 1 bonding wire was 1 cent. So by removing 1 pin, we saved 1 cent times 2. And if you consider that these sensors we named Rambo, we made 3 billion of them, times 1 cent. So it's worth some engineering. Okay, so I want to thank all the people who helped me during my career. There are a lot, but the 3 most important ones are René Sommer, Daniel Borel, and Jean-Daniel Nicou. So thanks to them, and thanks to all the other people I worked for or with in Logitech, and helped me to do my job.
Thank you very much for the presentation. Do you have any question? This is your moment, don't keep anything. No? Okay.
Just have one. I noticed you have a real-time clock on the mouse. I believe some people know the real-time clock here in the back. You know. Was it made in Switzerland, yeah, the real-time clock?
The real-time clock for René mouse?
Yes, yeah.
Yes, it was an EM chip.
Yes, okay, because we have 2 persons from EM here.
Also, EM made the optosensors,
yeah.
the differential optosensors, they were also made at EM in Switzerland. And the chips have been made, are still made in Switzerland.
Okay.
But the packaging, of course, it's in the Far East.
Thank you.
Thank you very much again.